Right, let's talk about indicators. We've mentioned them before, and we obviously know that they change color and they show us the end point or equivalence point of a reaction. Okay, now typically they are weak acids. Sometimes they're weak bases, but usually they're weak acids. And the acid and its conjugate base must have different colors. Again, typically they're very complex organic molecules, they're large organic molecules, and larger molecules tend to absorb light in the visible spectrum. So they tend to be large organic molecules that are acids, and they have a different colored conjugate base. So this would be the weak acid. When we dissolve it in water, this equilibrium set up. This is its conjugate base. So this would be acid 1, base 1, acid 2, base 2. That's easy. This is my color 1. This is my color 2. The conjugate base is color 2. Okay? So where the equilibrium lies depends on Ka, doesn't it? The greater the Ka, the further to the right. Okay? In this case, we call it K in. The dissociation constant for this particular weak acid or indicator. Okay, so we could express its K in that way. Just the same as Ka, obviously, but it's just specifically relating to indicators. We ignore the water term. Now, I've never seen questions on this, but it's just to show you that the equilibrium constant of the acid is the indicator, obviously, and the bigger this is, the further it is to the right. So if it's a strong weak acid, then we're going to see more of color 2, and if it's a weak, we're going to see more of color 1, you guessed it. So there's the equilibrium, color 1 and color 2. Now I've just put in typical colors. This would be the colors of which indicator would be methyl red or methyl orange, wouldn't it? So color 1 and color 2. Which color would be seen if we add this indicator to an acid? Well, if we add it to an acid, then we increase the concentration of this. What does that do? It causes the equilibrium to shift to the left, and we see color 1, we see red. So acid would give color red. And you can fill that in your notes. If we add it to an alkali, what would happen? The alkali would react with the oxonium ions here and cause the equilibrium to shift to the right, so we'd see color 2. All of this fits nicely together with your theory about equilibrium. Oh, there it is there. There's the explanation for you. Just in case you didn't pick that up, you can copy that down. Okay, in your explanation, it's missing here, but you should say that in the case of adding to an acid, this is high concentration, so it will shift this equilibrium to the left. And if you add to an alkali, the alkali reacts with the oxonium ions, shifting the equilibrium to the right. Okay, that's that. So an intermediate color will be seen. So 50-50, remember, one of them, in the above case, this was red and this was yellow. So we'll see an orange color when these two are equal. Okay, that makes sense. So K in, at this point, if these two are equal, then they cancel, don't they, mathematically? So if they cancel, then at this point, K in or Ka equals the hydrogen ion concentration. If we can measure that, we can measure the Ka for that particular indicator. Okay. And we just said that that's what it implies, that we can measure this and we can find Ka for the indicator, or if we know Ka for the indicator, at that point we can deduce the concentration of the hydrogen ions, of oxonium ions. Right, a couple of notes. The Ka value determines the pH at which the color changes. Okay, so each color change will happen slightly different place for each indicator. It will depend on the indicator's Ka, which will obviously be different. And a complete color change needs a pH change of about 2 units. This is called the working range of the indicator. So for the indicator to go completely from one color to another, the pH has to change 2 units. And that's important. You're going to see why. We have our graphs, and we're going to talk about the working ranges of indicators. So we have to choose the right indicator depending on the strength of the acids and bases. Remember, this was strong acid, strong base, strong acid, weak base, weak acid, strong base, and weak acid, weak base. Let's have a little look at some of the data. So methyl orange, it changes color completely between about 3.2 and 4.5. This is called the working range of the indicator. So 3.2 to 4.5, it goes from red to yellow. Right, great. Where is that on these graphs? Well, we'll look at that in a second, but that working range has to coincide with the vertical part of the graph. Okay, it has to coincide with the vertical part of the graph. Phenolphthalein, pH working range is between 8.2 and 10. Again, it has to coincide with the vertical part of the graph. It goes from colorless in acid to magenta, pink in alkali. Bromothymol blue we don't use very often, but just to show another indicator, its working range is 6 to 7, so it's there, isn't it? So you could say which of these titrations we could use bromothymol blue in, and in acid it's yellow and alkali it's blue. Now, I've never seen you have to recall that particular fact, but yes, with methyl orange and methyl red, which are the same more or less, and phenolphthalein, you should remember the colors. So we have to think about suitability in these titrations. The working range has to fall in the vertical part of the curves. If it does, the indicator is suitable for the titration. So let's have a little look at this. Strong acid, strong alkali, all three of these indicators are suitable. Why? Well, because all of their working ranges fall into or coincide with that vertical range. Look, methyl orange 3.2 to 4.5 is there. So it will completely change color at the end point. Bromothymol blue is here and phenolphthalein is here. So all of them are suitable. With strong acid, weak alkali, that's this one, weak alkali, strong acid, then it's only methyl orange, because methyl orange is 3.2 to 4.5, and bromothymol blue, which is 6 to 7. This kind of falls there, doesn't it? Weak acid, strong alkali, so strong alkali is here. Really, the only one that's suitable is phenolphthalein. Is 8.2 to 10, which falls into here. So phenolphthalein with a strong alkali is the perfect indicator. And with weak acid, weak alkali, you can't use an indicator. You have to work with a pH meter. Right. What are the colors at the end point? Well, this is actually quite a tricky little question. With methyl orange, the color at the end point is a mixture between red and orange. So if we've got a red color, red and yellow. So if we've got a red color, as soon as we see a tinge of orange, then that's the end point. If we start from the other side and we start with yellow, as soon as we see a tinge of orange, that's the end point. With phenolphthalein, if we're starting with an acid, it will be colorless, so the end point will be the first permanent faint pink color. If we're starting with the alkali with phenolphthalein, then it will be pink to start off with, and the end point will be when the pink color just disappears. Okay, those are the two key ones to remember. Just something to mention before you go on to do some questions. Diprotic acids are a little bit more complex, and this sometimes comes up, but you just need to understand the overall process. So if we start with a diprotic acid like ethane dioic acid, oxalic acid, then there are two steps. There's a step to make this ion, or this compound first, okay? And then that continues to react with the sodium hydroxide to make the sodium ethane dioate. So the first step happens, so imagine we're adding solutions of equal concentrations here. The first step happens at 25 centimeter cubed of sodium hydroxide added, because it's a 1-to-1 mole ratio. So you get a little step there, and we could actually use an indicator to indicate when that first step is complete. Then the second step, if we keep adding the sodium hydroxide, we go up here, the second step is complete at this point. So the end point of the total reaction, the overall reaction, would be 50 centimeters cubed. Okay, and then the gradient goes up because it's a strong alkali and then levels off. One key question to answer here is, where is pH 7 on this scale? Where's pH 7? Have a think about it for a second. And pH 7 is there, because this is the overall neutralization of the ethane dioate. Once the second step is complete, then the pH shoots up and levels off because it's a strong alkali. Okay, right, got a few pages to read through there and answer the questions.